Section 12.3, Double Integrals in Polar Coordinates, Video 5. Let's do another example that doesn't look like polar coordinates, but will actually help us integrate it fairly straightforward. We're going to find the volume between two surfaces. We're going to find the volumes of the solid bounded by the plane z equals 0, in other words, the xy plane in 3 space, and the paraboloid z equals 1 minus x squared minus y squared. Had we not been told this was a paraboloid, we could still graph it pretty straightforward, as I'm going to show you in a moment. All right, so let's take a look at what this is going to look like in 3 dimensions. So let's draw our x-axis, our y-axis, and our z-axis. The plane z equals 0 is just a plane containing the x-y axis, so not a problem there. But as far as what the surface z equals 1 minus x squared minus y squared looks like, we can find the traces of this in each of the individual planes. For example, if we said let x equal 0, then we would get the equation z equals 1 minus y squared, or y squared equals, or z equals negative y squared plus 1. So in the yz plane, which would be the plane that you see if I draw the if I erase the x-axis, this would be an upside down parabola, opening in the z direction but downward, and then up 1. So if this were 1, then the trace of this surface in the zy plane would be that parabola. Now, where does it intersect down here? Well, we would just have to let y equal 0. And if you let y equal 0, we would have to let z equal 0. And if you let z equal 0 and solve 0 equals negative y squared plus 1, you get y equals plus or minus 1. So negative 1 and 1. What would the trace of the paraboloid look like in the xz plane, which is a little harder to draw because it's a little skewed? Well, we would have to ignore the y-axis and just let y equal 0. But because of the symmetry of this equation, we would get the exact same thing, just in the xz plane, not the yz plane. So we would get this upside down parabola that would hit the x-axis at 1 and negative 1 as well. This might actually come down a little bit more like that. I'm not good at drawing things in 3 dimensions. And we're bounding this below by the plane z equals 0. So what happens if we let z equal 0? Well, then we get 0 equals 1 minus x squared minus y squared. But if we move the variables to the left, we get the equation of a unit circle, which means on the xy plane, on the floor, if you will, this actually forms a unit circle, not the best unit circle I've ever drawn. So it kind of looks like, and I'm just going to hold up the book. This is on page 712, by the way, and I hope this is in the screen. But it kind of looks like that. Looks like a hat, or maybe an upside down bowl. Okay, so how do we find the volume between two surfaces? Well, we can integrate underneath the upper surface over the region in the xy plane. This is similar to saying, how do you find the area under a curve? You integrate that over this interval, and that'll give you the area. In 3 dimensions, to find the volume under a surface, which is precisely what we're finding here, you do the double integral over that region. Well, I'm going to call that region D for disk. Let's see, this is the circle defined by x squared plus y squared equals 1. So we're going to do the double integral over that region of this function, 1 minus x squared minus y squared dA, which looks like it's a pretty easy thing to integrate in terms of x's and y's. So why don't we just integrate it in terms of rectangular coordinates? Well, here's the reason why. When you integrate over a region, in this case, the region in the xy plane is this. If we were to integrate this, we would have to integrate it from left to right and from bottom to top. But we can't just say integrate both of them from 1 to -1, because that doesn't define this region. If we only integrated the x's from -1 to 1 and the y's from -1 to 1, that would actually be integrating over this square, which we're not. So how do we make an adjustment for that? Well, we would have to pick one to integrate over numerically and the other one to integrate over in terms of functions. For example, if I wanted to integrate the y's, let's think about a representative rectangle here. This rectangle would slide back and forth from -1 to 1. But what bounds it from above is not just a number. What bounds it from above is the equation of the top half of this circle. If you solve this for y, you would get y equals the square root of 1 minus x squared. What would the equation of the bottom half of the circle be? The same thing except negative. Y equals negative square root of 1 minus x squared. What that means is if we were to try to integrate this in terms of rectangular coordinates, integrating the integrand would be easy. We'll do dy first. If you ever set up a representative rectangle in a region to figure out how to set up the limits of integration on a double integral, the last thing you integrate with respect to should correspond to the thin dimension on this rectangle. Since it's thin in the x direction, the x's are sliding between -1 and 1. The first thing you should integrate with respect to is the direction that dictates the longer dimension of the rectangle. So we would integrate with respect to y's first, and those would be the functions that define the top and the bottom of this rectangle as it slides back and forth. So if we integrated with respect to y first, on the bottom, this region is bound by the equation y equals negative square root of 1 minus x squared, and on the top, the region is bound by the equation y equals positive square root of 1 minus x squared. And then the x's would just go from -1 to 1. So could you integrate this? Possibly. It might be a little ugly. It might invoke some messed up trig substitutions. Just looking at it, I'm not looking forward to it. However, we can avoid all that. Why can we avoid all that? Or more specifically, how do we know that polar coordinates are a good idea here? Well, there's actually two things. Number one, in the integrand, you have negative x squared and negative y squared, which is the same as the opposite of the quantity x squared plus y squared. We can replace x squared plus y squared with r squared. But the other thing that says do this in polar coordinates instead of rectangular coordinates is this region is ridiculously easy to define in terms of polar coordinates. Let me redraw this region. In terms of rotating, I can get to any point between here and here by saying the radius has to be between 0 and 1, and I can make a complete revolution. Now that's not part of the picture, that's just me drawing an arrow indicating that I'm rotating around. This circular disc, in terms of a polar rectangle, the radius is between 0 and 1, and the angle is between 0 and 2 pi. I can get to every point on there by going out a certain radius and rotating a certain angle as long as the radius is between 0 and 1 and the angle is between 0 and 2 pi. So the limits of integration would be constant. That's going to make this a lot easier. We just have to convert this to polar coordinates now. All right. As I already mentioned, x squared plus y squared collectively is r squared. So we can change negative x squared and negative y squared to negative r squared. The dA in polar coordinates is r dr d theta. And now this is going to be easy to integrate. Our radii are going from 0 to 1, and our angles are going from 0 to 2 pi. So this will be much easier to integrate. Let's focus on the inner integral first, and then we'll import the results back into the outer integral. So the inner integral, I'll go ahead and distribute the r. Integral from 0 to 1 of r minus r cubed dr. So the integral of r is 1/2 r squared, The integral of r cubed is 1/4 r to the 4th. We're evaluating that from 0 to 1. If I substitute 1, I get 1/2 minus 1/4. And if I substitute 0, I get 0 minus 0. So the 0 is not going to matter here. Word of warning, you can't always just disregard a 0 as a lower limit of integration. Sometimes when you substitute it into the integrated function, you do get 0 and therefore it vanishes. But there are some functions where plugging in 0 does not produce a value of 0. So don't always just say, it's a 0, I don't need it. Sometimes you do. In this case, not really. 1/2 minus 1/4 is 1/4. Oh, this is going to be so much easier now because the value of the inner integral is a constant. There are no thetas, which means as I move to the outer integral from 0 to 2 pi d theta, the value of the inner integral is just 1/4. Well, it's easy to integrate a constant. The integral of 1/4 is 1/4 theta. We evaluate that from 0 to 2 pi. So 1/4 times 2 pi minus 1/4 times 0. That disappears and I'm left with 1/2 pi or pi over 2. A much easier integral to evaluate in polar coordinates than in rectangular coordinates. And again, there were two things about this integral that said tripolar coordinates. Number one, the presence of the x squared plus y squared. I know it was a little stealthy because they're both negative, but this is the same as 1 minus quantity x squared plus y squared. The presence of that said, hey, I can replace this with just an r squared and be down to one variable. But the more important thing is the region was very easy to define in terms of polar coordinates as opposed to define in rectangular coordinates, making the integration a lot easier to evaluate. Or rather, I should say, making it easier to evaluate after we integrated. Substituting and converting to polar coordinates doesn't always make the integral easier. See the last example, but in this case, it made it much easier.